Yeah. So we finished last time on Wednesday with fundamental theorem of calculus part 2, which is the evaluation theorem, how you can evaluate a definite integral. And that's the really big one. But in class today, you saw a lot of time spent on part 1, which I admit it is a very weird, confusing theorem. So let's do a couple problems on this and hopefully shed some light on this. Back to part 1. And part 1 involves how do you take the derivative of an integral? An integral where one of your lower bound is a constant, your upper bound, that's what we call these numbers, or upper limit, is x in this case. And that means you have to use a different variable to talk about your function because you've already used x up here, right? And what she did with one of them, she said it in words, but it would have been nice to write this out so that everybody understood what she was talking about. You can, for some of these, you could evaluate the derivative in one of two ways. Now that you know part 2, the evaluation theorem, how to evaluate an integral, we could do that first, now that we know how to do it, okay? And then part B, which we'll do afterwards, is just straight up using fundamental theorem of calculus part 1 without evaluating the integral. And I'll show you, by doing it this way, you do kind of, it maybe makes a little more sense why this works, but I also have a warning for being able to do it this way, which I'll talk about in a second. So by evaluating the integral, what I mean is, the first step to evaluate a definite integral is to find your, so this is still f of x. I'm just going to evaluate the integral. Your antiderivative of cosine of t is sine of t. And what we talked about last time, you could put plus c, right? When you do an antiderivative, you could put plus c, but it is always going to cancel out when you have a definite integral. So we won't do it here. And we're going to evaluate that just to emphasize this. This is from t equals x to t equals 2. These, even though they don't write it here, these are t limits. And so if I do that, that gives me, the top one goes in first, that gives me sine of x minus the sine of 2. This would be 2 radians, sine of 2 radians. Okay, so this is still f of x. That's just what this equals if I actually evaluate it. The direction said to find f prime of x. So if I then take the derivative of this answer right here, the derivative of sine of x is cosine of x. And what you have to wrap your head around is that the sine of 2, if you wanted to know what that was, you would plug it into a calculator. And everybody's calculator should give the same answer, which means by definition, the sine of 2 is what? Well, what's the, okay, well, yeah, you're right. The derivative is going to be 0, but what is the sine? Why? Because the sine of 2 is a, if everybody's calculator gives you the same answer, doesn't that mean it is constant? It's always the same, right? What does constant mean? Nothing changes, right? This is a constant because there's no x or anything in there. That's a constant, and we know the derivative of a constant would have been 0. Yeah. So then that's our answer. The derivative of this integral is just cosine of x. And I think there's value in doing it this way because, for one thing, it helps you. So now let's do it the fundamental theorem of calculus way, because remember, I'm going to use this space up here so I don't have to move my paper. The fundamental theorem of calculus part 1 says if you have an integral from a constant to x of any function of t or some other variable, this is f of t, not f of x, sorry, f of t, that to take the derivative of this integral, it's simply just going to be f of x. It's as easy as just plugging in x for your t right here. It's just going to be cosine of t. Cosine of x. I said replace your t with x, and then I wrote t and said t. It's just cosine of x, which is exactly what we got here, right? And one thing I guess that helps you understand is why that lower bound doesn't matter, right? Because you can tell if you did it this way, the lower bound's just going to end up being a constant and the derivative of that would be 0. So that's one thing it does shed light on. You have to admit, if you just go straight to using the fundamental theorem of calculus part 1, this is faster, right? This is faster. It is a little more mysterious, right? Like, whoa, you can just do that, right? And maybe this makes more sense, right? By just doing the integral first and then taking the derivative. But here is why what she said something in class, like you really need to know how to use that theorem. Here is why. Here's the answer to why. Because you might be saying, yeah, okay, Grant, I get that seemed a little bit easier, but this makes more sense to me. And I agree. I do not disagree with that. I think this makes more sense. However, the types of problems that they usually give you involving the fundamental theorem, the one she gave today was an exception, at least the first one she talked about. Most of the ones that show up in the book and on tests, they do this for a reason. They don't want you to do, they want you to go straight to the fundamental theorem of calculus, and here's why. If I wanted to find the antiderivative first and then take the derivative, I would be stuck. And the reason why is, and this is hard because you're just learning about antiderivatives. We spent one day on it, the first day of class, we practiced antiderivatives, maybe 2 days. But what I'm here to tell you is that unlike in 17a, don't you agree in 17a, once you learned all your rules, there pretty much was not a function you could not take the derivative of. You might have to use a product rule, you might have to use a chain rule, you might have to remember a derivative formula for a sine or a trig function. But once you knew all those, everything had a derivative. But the opposite is not true. In the world of antiderivatives, there are lots of different functions that have no antiderivative. And this is a classic one right here, e to the t squared. I'll say I would be stuck because e to the t squared has no antiderivative. And so you could not do it that way. You couldn't take the antiderivative and then plug in and then take the derivative of that. So this is kind of forcing you to use the fundamental theorem of calculus part 1. So we must use FTC part 1, which says to take the derivative of this integral. Okay, and also we did talk about this on Wednesday. Notice I have more than just x here, more than just x, but I'm still going to this doesn't matter. I'm just going to plug that in, e to the sine of x squared, and by the chain rule, I want to multiply by the derivative of my stuff. So this is going to end up being times cosine of x. All right, so yeah, unfortunately, you may be, you're going to have to use this theorem. You may not always be able to find the antiderivative. Okay, the other thing that came up in class that I thought I would mention that might help a little bit was Dr. Burke spent some, there's no examples in the book. This is why I didn't give you any on Wednesday. Oh, cosine. That's because when this is just x, we just put that in, right? And that's your derivative formula. So just like in 17a, anytime you replace what used to be just an x with something that's more than x, then you have to follow it up with the chain rule. You still plug that in, but then you have to multiply by the derivative of your stuff, the stuff that was more than just X. That's why we're following it up with that. We're going to see that again over here on this problem too. So yeah. Okay. There's no examples in the book. All the examples they have in the book, they are where there's a number here, and they do sometimes have like where you have to use the chain rule here. But there's none in the book where both of these are functions, which is why I didn't show you that on Wednesday. And she spent some time at the beginning convincing you that when you see this, you just put this in, multiply by the derivatives. And I thought that was a little bit, I had a little hard time wrapping my head around that. So let me give you another explanation for this, okay? And let me set this up here with one of your properties of integrals. So this is my little scratch space over here. If you wanted to, let's say I had some function here, and let's say I wanted to know the integral from 1 to, let's say, 10. Let's say, oh, that's because of the. Let's say I wanted to know the integral from 1 to 10 of f of x dx, which means I want basically this area, right? If I wanted to, couldn't I pick any number between 1 and 10? You know, pick your favorite number. Let's say I pick 7. If I wanted to, couldn't I find this area and then add it to this area? And that would give me the same. That would give me the total area. I could break this up if I wanted to as the integral from 1 to 7 of f of x dx, and then add the integral from 7 to 10. Does that make sense? And I just chose 7 randomly. I could pick any number between there. Right? If you think about just accounting for area, that would seem to make sense. So here's the way I choose to think of this. Between my lower bound, x squared, and e to the x, remember that what do variables stand for? They're just numbers, right? So say, for example, x was 1. If x was 1, example, if x is equal to 1, 1 squared is 1, e to the x is e. My point here is, how many people agree between 1 and e, there's a whole bunch of different constants. I'm just going to call it c. There's all kinds of numbers between 1 and e, right? So, and that would be true no matter if I picked x equals 2, 3, 4. So what I was going to say here is between x squared and e to the x, there are lots of constants. And so here's what I'm going to do. That means I could rewrite this integral, the integral from x squared to e to the x. If I go from, so pretend this is really x squared, right? This is x squared and this is e to the x, right? I could do the integral from x squared to some constant.
Do you mind moving the paper?
Oh yeah, that would probably be a good idea. Yeah.
Okay.
Thank you. Thanks, Maya. So let me backtrack here. If you agree that if I picked the numbers for x between x squared and e to the x, I could find a whole bunch of constants. I'm going to then break up this integral, kind of similar to this. I'm going to integrate from x squared to c, and then add to that from c to e to the x. In the same way, if I wanted to between 1 and 10, I could just break it up from 1 to 7 and then from 7 to 10. It's the same exact idea. Now, why did I do that? How many people agree this looks more like what we've been doing for taking derivatives of, right? Where you have a constant to a function. We know how to deal with that with the fundamental theorem of calculus. Now, there is an issue here, but I think you know how to handle it. When you use part 1, you want the variable up here and the constant down here. So what am I going to do with this one right here? if I flip this, I'm going to put a, yeah, I see it in the, I'm going to put a negative, huh? And then I'm going to take the derivative because this is what I wanted to find the derivative of. So we're going to take the derivative with respect to x, but we have to do it for both of these. So by the fundamental, this is another one, by the way, I was mentioning before, this function right here does not have an antiderivative that you will ever be expected to find in the 17 series. Unlike e to the t squared, it actually does have an antiderivative. We'll never discuss how to find it. So just assume you can't find the antiderivative of that. But so we have to do the fundamental theorem of calculus, which says we're just going to plug that in for t. So it's going to be x squared squared. And then using the chain rule, this is more than just x, so then I have to multiply by 2x. And then same thing here. That's going to go in for t. And by the chain rule, since that was more than just x, I have to multiply by the derivative of e to the x, which is e to the x, and that's my derivative. Okay. Let's do this. I'm going to skip order here, so don't worry about the number. Well, no, the number actually worked out. Huh. What do you know about that? That was problem number 3. I wasn't planning on doing it in this order, but that's okay. I believe at the end of class, I left a little early to get ready for this. She did something similar to this. Basically trying to illustrate now, what can an antiderivative do for us? We know that the area under a velocity curve is distance, right? Okay, big deal. How many times are we ever going to need that, right? But as we'll move forward, we're going to start to see all of these uses for finding antiderivatives. This one isn't super exciting, I guess. So we don't actually have any numbers, but it does give you an idea of where you could use an antiderivative here. This is actually number 47. I think that was one of the problems she had recommended you looking at. Yeah, okay, so anytime I do this, that's the book number. This is in 5.3 number, that's the problem number, 5.3, number 47. Yeah, I try to pick some problems from the book too. So what this says is if w prime of t, which we know now how to interpret a derivative from last quarter, that would be like the rate of growth of something. And what this is measuring is, let's say w prime is the growth rate, how fast the child's weight is changing over time per year. And the question then would be, well, what does this definite integral mean? What would it mean? What would that integral represent? So we're not really looking for an answer necessarily, a numerical answer. We're looking for more of a description. What does that mean? And we could approach this then. We know by the fundamental theorem of calculus, part 2 now. I should have done, well, we already did one with part 2. We did one with part 2 where you actually evaluate it. Your first step would be to find the antiderivative. Well, let me ask you this. What is the antiderivative of the derivative of w? Because that's what this is, right? That's the derivative of w. That's just w, huh? The antiderivative of the derivative is like it cancels out, huh? So by fundamental theorem calculus part 2, the antiderivative of W prime of t is just W of t. It's just undoing the derivative. So this would represent W of t. Now, what would that represent? That represents the weight of the child at any time t, not the growth rate, but the weight of the child, right? W prime is a rate. It's how fast it's growing. And we know by the fundamental theorem of calculus, I would then evaluate that from t equals 10 to t equals 5. And so that would give me W of 10, whatever that happens to be, minus W of 5. And so the question is, what does this represent in words? You've probably got this sense already, but unlike a lot of last quarter, if you had Dr. Martinez, I think more here, there's going to definitely be some numerical things you have to do, right? Come up with a numerical answer, but a lot of being able to explain is what you probably got the sense that Dr. Burke wants you to be able to do. What does that represent? And maybe we'll start by giving this a meaning. Remember, we undid the derivative, right, by finding the antiderivative. So this is the weight of the child. Child has an L in there. At time t. So then if that's the case, what does this represent? This represents the child's weight. I am having trouble. That was supposed to be an apostrophe. Child's weight, that's not an E there. At t equals 10, this represents the child's weight at t equals 5. And so what is this minus this? What does that represent? Isn't that the net change, the difference in the weight of the child between 10 years and 5 years, right? So together, this represents, if I put this together, this represents the net change in weight of the child from 5 years old to 10 years old. Does that make sense? If you took your weight when you were 10 years old and subtracted your weight when you were 5 years old, that's going to tell you your net change in weight. Oh, it would make sense if you could see it though, huh? And that was something else she mentioned too in class, that a definite integral can give you like a net change in something. How much something changes in a period of time, if that's what we're talking about. Here's another one. This is number 53. And it says, oil is leaking from a tank at a rate of R of t, gallons per minute at time t. What does the integral from 0 to 120? I think t was measured in minute. Oh yeah, per minute. There we go. Yeah, it's in there. What does the integral of that R of t dt represent? And what might be a little helpful here, I chose this one for a purpose because it's not exactly like this one. The one we just did here, we were given the derivative, the growth rate, right? It was a derivative already. They've described oil leaking from the tank at a rate of R of t, but how many people agree this must be the derivative, right? If this was a rate, this must be a derivative because it's something, how fast something was changing. So what if we let A of t equal the amount of oil at time t, then what would R of t be as a derivative? Wouldn't you agree that R of t then must be the derivative, of A of t? It's the rate of change of the amount of oil that is leaking from the tank, right? Rate of change of amount of oil of A of t. And that might be useful then, because then if we then just thought of R of t as A prime of t, it's going to feel more like the problem we just did. Because the antiderivative of the derivative is just going to give me the amount A of t. And then by the fundamental theorem of calculus part 2, I would evaluate this from 120 to 0, which is A of 120 minus A of 0. And what does that represent? Kind of like the change in the weight of the child. This would be the amount of oil that is leaked out after 120 minutes minus how much is leaked out at the beginning. So this is the net change in the amount of oil that has leaked from t equals 0 to t equals 120 minutes. Which I suppose is really the total amount then, It's the total amount of oil, because we assume there was none. Sorry, I gotta keep my eye on the screen there. So hopefully you're picking up on something, because there's a whole variety of these problems in the book. I think she has even more that she's assigned. Are you picking up on something that if you do the definite integral of the derivative of something, all that really represents is the net change in this case, just A of t from 120 to 0. If you do the integral of W prime of t, the change in weight from 10 to 5, all that represents is the net change in weight from 10 to 5 or 5 to 10, whichever way you want to go. Right, so that's how this works. Questions? What made this one a little hard, they didn't tell us this, so we had to come up with our own and view that as a derivative. So you had to do that on your own so that it looked like the same type of a problem. Okay. So let's switch gears a little bit and let's talk about now just evaluating integrals using the fundamental theorem of calculus part 2. And this is going to help answer, I was peeking at the WebWorks homework, which you should all be doing as well. And there's one question that I kind of anticipated I'd get a lot of questions on. So I kind of wanted to head that one off here. So let's say we want to just evaluate this integral. We're not going to attach any meaning to it. The integral from 1 to 3 of 3x times x minus 4. And then we're going to sketch out what we're finding. So let's do the sketching part first. If you were to multiply this out by distributing, that gives you 3x squared minus 12x. Graphically, what is this the graph of then? If it has an x squared in there, what's that the graph of? Good. Yeah, that's going to be a parabola. And the easiest way I'm going to graph this one is when it's in factored form, if you set this equal to 0, you should be able to tell that you're going to have an x-intercept at 0 and also at 4. And we know it's an upward facing parabola, so I know that this parabola is going to look something like this. Now this integral that I'm trying to evaluate goes from 1 to 3. So if you think about that on your graph, here's maybe 1, here's maybe 3. The integral has something to do with this shaded region right here. And what I want to remind you from earlier this week is, who remembers, if the area, if this region that's the graph is below the x-axis, what do I expect? What kind of an answer do I expect to get out of this? It's going to be negative. Yeah, it all goes back to this is really what you would get if you did all your whole Riemann sum with all the rectangles. And if you did f, part of your Riemann sum involves f of x sub I, you would get a negative value here. So this whole thing is going to come out negative because graph is below the x-axis. So let's confirm that. Let's do the integral. That's the easiest way to make sure that it comes out to be negative. And so to do this integral, this goes back to day 1. What is it? Section 4. You remember the first day we did antiderivatives, right? We didn't have an integral there, but we were asked to find antiderivatives. And remember, if you've got a product and you're asked and you need to find the antiderivative, you can't just find the antiderivative of that and multiply it by the antiderivative of that. That wouldn't work for derivatives, so it's not going to work with antiderivatives. So what you would want to do is actually distribute it like I did here. So we're going to have the integral from 1 to 3, 3x squared minus 12x. Using fundamental theorem of calculus part 2, first step is to find my antiderivative. The antiderivative of 3x squared is 3x cubed over 3, which actually is just going to be x cubed, isn't it? Because that's going to cancel. Your antiderivative of minus 12x is minus 12x squared over 2. So let's just rewrite this. This is really just x cubed minus 6x squared. And then I evaluate it. You don't need to put your plus c when you're doing these. Evaluate it from 3 to 1. 3 goes in first. Minus the 1 is going to give me 1 cubed, which is 1 minus, I can tell that's going to be 6. 27 minus 54, I believe, is negative 27. This comes out to be negative, the whole thing is negative 27, minus negative 5. Negative 27 minus negative is really adding, so my final answer comes out to be negative 22, which, as we expected, it's negative because my graph is below the x-axis. This wasn't the problem. This right here is not where I'm anticipating a lot of questions. It's my follow-up question. So we know that's going to be negative. Why did we divide by 3 and 2? Remember your antiderivative, if you're finding the antiderivative of x to a power, back on the first day, we just wrote little f of x and capital F of x. That's where you add 1 and then divide by the same power. And the constants can just stay there. So I left the 3 there, added 1, and then divide by the same power. This is the, okay, maybe I need to write that down. I'm finding the antiderivative, yeah. Yeah, so now, okay, and I guess I haven't even really mentioned that. Now we can, when we see an integral sign, that is another, basically, we're just going to associate that now with antiderivatives, right? That's going to mean finding your antiderivative. Okay, now say for this same function, 3x times x minus 4, the question I have for you is, if I left this upper limit, if I called it a, and I asked what value of a will minimize the value of this integral. Here's what I mean by that. I need to redraw my graph. So here's what I mean by that. We just did the integral from 1 to 3, and we found out that the value of this integral came out to be negative 22, okay? What would happen if I kept going a little bit further? Remember, this point right here is 4. What if I went to 3.5, 3.5 here? So I went a little bit further. What do you think would be, would the value of the integral from 1 to 3.5 be more or less than negative 22? Would it be more negative or would it be closer to 0 if I went from 1 to 3.5? How many people agree with, since this is negative 22, if I keep going here, this is going to make this even more negative, right? I'm going to be adding more negative values here. So I don't know what it's going to be, but it's going to be negative 25, let's say, right? Now, and then if I kept going, I'm getting more negative area, right? But what happens after I pass the 4? If I kept going past the 4, what kind of area would I get there? That's going to be positive. So if I integrate past 4, I'm actually going to get bigger values, right? This is going to come out to be positive, which is going to counteract some of these negatives. So if I started at 1, where should I stop so that I get the most negative, right? By minimizing, in this case, what we want is the most negative answer. Where should I stop? How many people agree if I stop at 4, then that's going to be as negative as it's going to be, huh? And if I go past 4, then I'm going to start getting positive numbers, which is going to make it not so negative. So I don't think you have to show any work on this. I think this question on WebWorks is really just getting you to draw the graph and kind of think about where things are positive and negative. And so we'll just say A equals 4. And we could say if A is greater than 4, then we start getting positive values for the integral. So yeah, anyhow, if you looked at the WebWorks, you'll know there's one kind of similar to that, except that one actually asks what value of A would maximize the integral, but it's kind of the same idea. If you sketch out the picture, you should be able to answer that question. No, yeah, so the way it works, I know it's weird. This is always your lower numbers on the bottom, and this is your right. The A is the one on the right. This is your right, and that's your left. Okay. Let's close with these two problems here. In 5.3, actually towards the beginning, I'll just flash my book up here. Since in the reading you learn how to evaluate a definite integral, you've got like 28 definite integrals here to evaluate. That's a lot of problems here. She gave you some to practice and suggested some. So let's practice a couple of definite integrals, and the skill we're going to be working on now for the next few sections is improving our, you know how we started by finding antiderivatives. We started this whole class with that, and we learned a few tricks, but there's more tricks of the trade, I guess, in terms of finding antiderivatives, which we're going to be working on in the next few classes. This first one we did talk about. I remember on day one. So we want to evaluate this integral, so we need the antiderivative of this. And my hint is the same as I would give if I asked you to take the derivative of that. If I asked you to take the derivative of it, you could absolutely use the quotient rule, but I would hope you wouldn't, because there's an easier way. How would you make this simpler to deal with if you were even just taking the derivative, not the antiderivative? What would you do? Since there's one term in the bottom, yeah. Anytime there's one term in the bottom, we're going to split it up. Split up. And that's our familiar heart thing. You break this up. Oh, my pen just flew off in the air. So we're going to have x over root x minus 1 over root x. And then we want to, simplify this. This is really x to the first over x to the 1/2. If I subtract the exponents, that's just going to be x to the 1/2. And if I wanted to integrate 1 over root x, I would want to rewrite that as x to the negative 1/2. So this is just a rewrite. And now I'm ready to find my antiderivative. So by that power rule, I'm going to move this over here so I have more room. Remember, you add 1. That's x to the 3/2. And then I'm going to go ahead and write it this way for now. And then you divide by that. Add 1 to x to the negative 1/2. That gives you positive 1/2. Divide by 1/2. Again, for these with definite integrals, you don't need to put the plus c. We're just going to evaluate this from 9 to 1. I'm going to clean this up, though, before I plug in. If I'm dividing by 3/2, that's the same thing as multiplying by 2/3. And dividing by 1/2 is the same thing as minus 2x to the 1/2. Nine goes in first. Remember, x to the 1/2 is really just square root, so I'm just going to write it like that. Minus, plug in the 1. If it's been a little while, remember that to do something like 9 to the 3/2, I'll put that up here. That's the same thing as the square root of 9, and then you cube the answer. This tells you the root, that tells you to cube the answer. So that is 3 cubed, that's going to be 27. This is just 2 times 3, so minus 6. Minus 1 to any power is just 1. So then this is minus 2/3 minus 2. Okay, this is, that's actually 3 goes into 27 9 times. So 2 times 9 is 18. 18 minus 6 is 12. minus 2/3. If I distribute the minus to both of these, that's really plus 2. 12 plus 2 is 14 minus 2/3. 14 minus 2/3 should be 13 1/3. Just a lot of fast number crunching there. And then last one I selected, trying to pick ones that I thought might be a little bit, I mean, there's lots of them there that could be troublesome, but this one might be troublesome because, so remember, if you have a constant, you could always, if it's times, right? If I think of this as 4 times 1/1 plus t squared, I can pull constants out. So if the constant's messing up, just bring it out of the integral. Why did I rewrote it the other way? I don't know why. It's t squared plus 1. Luckily, it's the same thing. 1 plus t squared is the same thing as t squared plus 1. But I selected this one to remind you of your antiderivative because it's not something we worked with a whole lot last quarter. Who remembers what function from 17a had a derivative of 1/x squared plus 1? ln's derivative is just 1/x. Yeah, it was a sneaky one. It's arctan. Yeah, it's arctan. Arctan or inverse tan, either way. So I thought this one might give trouble. So this is going to be 4 arctan of t. Remember, arctan is also known as AKA tan inverse. Either way you want to think of it. And then I'm going to evaluate it from 1 to 0. So if I plug in the top number minus the bottom one number, I've heard some students express some concern on trig, and I get it. If it's been a while since you've done some trig, that could be a little bit troublesome. If you're rusty on your trig, it's probably not going to be, that's probably not what's going to do in your grade. You might miss a few points here and there, but it's not going to be just because you're not so good with your trig. At the very least, if this was a quiz question and you got to hear and you're not sure how to deal with arctan of 1, just leave it like that. You're gonna, maybe they take off 1 point for not simplifying further, but it's better than missing the whole thing. But anyhow, how do you figure this out? What the arctan in this case of 1 means, when I see arctan in 1, here's the question I ask myself. What this is saying is, what angle has a tangent of 1? That's what that's basically asking for. And if you think of it that way, and at least if you can remember your triangles, because I teach trig from the triangles, there's 2 big special triangles. One of them, so this is going to be an angle, which we usually would call like theta, right? That's an angle. So if this was theta, if the tangent of theta, if the tangent of this angle is 1, and I could always think of 1 as 1/1, opposite over adjacent, 1, 1. If you did a Pythagorean theorem, you would know this is √2, but more importantly, what is this angle? Correct. It is 45 degrees. Probably want to do it in radians, which is pi/4. Yeah, pi/4. So this just becomes okay. How about this? This is asking what angle has a tangent of 0. Yeah, there's lots of ways to answer these questions, but the way I would have probably thought of it, and I know if you were one of my students and I taught you some trig, I want you to know what the graph of tangent looks like. And the graph of tangent has some vertical asymptotes. Here's tangent of x. And the tangent of 0 right there, right when x is 0, the tangent of 0 is also 0. So that part gets wiped out. 4 times pi over 4 gives us an answer, final answer of just pi. All right, folks, I hope you do some practice over the weekend. Do some of those problems that C suggests, even if you don't have to turn them in. Definitely look at those. And we'll get you ready for Wednesday, I guess. Yeah.